A new moon has suddenly appeared near Earth. A celestial event so improbable, so delicate, it shifts our understanding of planetary mechanics. Except, it's not orbiting our planet. It's orbiting the moon. What? A moon having its own moon? A submoon. A moon. This is the ultimate astronomical rarity. How did this mini-moon form? Is it here to stay? And, crucially, how would this bizarre gravitational dance affect us on Earth? Before we throw ourselves into the orbit of our planet's largest natural satellite, we must first understand the titanic forces that shaped the moon itself. If the mysteries of the cosmos and the science of impossible scenarios keep you gazing upward, you are in the right place. Subscribe to Stellify Science and hit that notification bell. We dive deep into the what-ifs that redefine our universe every single week. Now, let's begin our journey back in time to the creation of the moon, to understand the forces at play. Let's step back about 4.5 billion years, back to one of Earth's most impactful moments. Scientists theorize that in the early, chaotic years of our solar system, there was another massive protoplanet in our cosmic neighborhood known as Theia. This world, potentially about the size of Mars, was locked in an unstable orbit. We have no direct physical evidence of Theia today, because it no longer exists. This brings us to the most widely accepted hypothesis, the Great Impact Hypothesis. According to this theory, Theia and the early, newly formed Earth were both in orbits that doomed them to a catastrophic, head-on collision. When these two massive celestial bodies, already heated by gravitational compression and radioactive decay, smashed into each other at high speeds, the impact was, well, as the name suggests, truly great. The energy released was staggering, equivalent to trillions upon trillions of megatons of TNT, instantly vaporizing much of Theia and a significant portion of Earth's own mantle. Enormous amounts of material, molten rock, dust, and gas, were ejected from both planets. This wasn't merely debris drifting off into outer space. Instead, the gravitational field of the now battered Earth captured this material, forcing it into a dense, superheated ring of plasma around the planet. Over the course of a few million years, this ring of material began to rapidly cool and lump together. Under the relentless forces of Earth's gravity, this debris merged into one single massive object, an object we know today as the moon. The moon's distinctive composition, specifically the similarity in oxygen isotope ratios to Earth's mantle, is one of the strongest pieces of evidence supporting this titanic singular impact event. So, if that is the story of how our gravitational companion came to be, does the formation of a submoon mean we should be bracing for the Great Impact Round 2? Thankfully, no. That's not the only way moons can form. And by moons, I'm of course referring specifically to submoons or moons, which are all just different ways of saying a moon orbiting a moon. Still with me? Okay, good. Beyond the catastrophic Great Impact Hypothesis, which requires millions of years to play out, there are much faster routes to acquiring an orbiting body, specifically, the mechanism of gravitational capture. Some moons are fully formed, independent objects, asteroids, comets, or rogue dwarf planets that are pulled in by the intense gravitational forces of a larger celestial body. Take Neptune's moon Triton as a prime example. Triton is theorized to have been a large, icy body in the distant Kuiper Belt region. It may have been captured by Neptune's massive gravity after a close, delicate encounter. This gravitational disturbance, what is known in orbital mechanics as a three-body problem, could have ejected the object from its original solar orbit and pulled it into Neptune's own. Over immense periods of time, Neptune's tidal interactions forced Triton's orbit to go from long and elliptical to nearly circular. And in case you're wondering how this capture theory came to be, it's because Triton, unlike all other large moons in the solar system, orbits in retrograde. No, that doesn't mean its vibes are off, like when Mercury is in retrograde. It means that it orbits in the exact opposite direction that the planet spins in, a clear signature of an object that was forced, rather than formed, into orbit. In order to avoid the mess of a giant collision, let's imagine that our moon's moon was a captured object, like Triton. Perhaps it was once a typical kilometer-sized asteroid that passed just close enough to Earth to avoid a collision, yet even closer to the moon to find itself suddenly trapped in its orbit. This would be an incredibly delicate gravitational balancing act, a three-body challenge on an entirely new scale. The object would need to be massive enough to be locked into the moon's gravity, yet small enough not to disturb the moon's primary orbit around the Earth. The asteroid would need to be a true Goldilocks object. The moon's immediate gravitational influence, its Hill sphere, is small relative to Earth's overwhelming pull. If an object is too far from the moon, Earth's gravity immediately snatches it back. If it is too close, tidal forces will rip it apart or force a collision. One study suggests that in order to maintain a stable, long-term orbit around our moon, this object would have to be no bigger than about 1 kilometer in diameter. At this small size, the gravitational forces holding it to the moon are tenuous at best. Even if this asteroid were to succeed in becoming a moon, its tenure in the lunar sky would be short and volatile. It wouldn't stay one forever. This tiny submoon would be constantly tugged and pulled in different directions by the competing, massive tidal forces of both Earth and the moon. The forces acting on it would be extreme. The moon's gravity, trying to keep it in a perfect circle, and Earth's immense gravity, constantly trying to stretch that circle into a wildly unstable ellipse. That constant gravitational tug of war means there would be a high probability of one of three outcomes. Ejection. It gets flung out of the moon's orbit and back into an unstable orbit around the Earth, or worse, directly into the sun's orbit. Collision. The orbital instability causes it to spiral inward, eventually colliding with the moon itself. Spiral to Earth. A slight critical shift in momentum places it on a collision course with our planet. Its entire lifespan as a submoon might only end up lasting a few years or, at most, a few decades. During this short window of time, the moon would have little to no measurable physical effect on us back here on Earth. Well, physically at least. But that wouldn't mean that it wouldn't become an object of endless global fascination. Throughout human history, the moon has been a source of inspiration for myths, legends, and folklore. The sudden, visible appearance of a tiny, swiftly moving satellite swinging around it would inspire a whole new wave of stories, art, and undoubtedly, plenty of conspiracy theories. The global zeitgeist would instantly have a new mystery to obsess over. Beyond the stories we'd get to tell future generations, scientists would have an unprecedented opportunity to study a complex celestial phenomenon, the three-body problem, so close to home. Observatories and space telescopes could focus on this tiny object to study the precise ways that different masses interact under such extreme gravitational competition. This would help us collect invaluable data on tidal dynamics, orbital decay rates, and the limits of a planetary body's influence. This data would be crucial for predicting similar events happening in the far-reaching, unstable parts of our cosmos, such as the asteroid belt or the Kuiper belt. But mostly, it would give you something new and exciting to gaze endlessly at in the night sky. The submoon's beautiful, brief tenure would eventually end. It would either appear to drift away, back into the depths of space, or careen downward into a rocky impact. The scenario that concerns us most, however, is the catastrophic conclusion. Amid the tidal tug-of-war between our planet and the moon, there's a chance that the moon eventually shifts course and collides with us here on Earth. In this event, the submoon, a 1-kilometer asteroid, would behave just as you'd expect any massive, high-speed object to act when it targets Earth. Headed toward Earth, it would enter our atmosphere and then begin to generate intense heat as it encounters the friction of the air. Considering its small, 1-kilometer size, there's a good chance it would likely break apart into thousands of smaller, flaming fragments before making a devastating impact on the ground. This fragmentation would result in a massive airburst, similar to the 1908 Tunguska event, which flattened 2,000 square kilometers of Siberian forest. But if it stayed intact, which is possible for a dense metallic or stony asteroid of that size, well, that could spell global trouble. Traveling at an average speed of 72,000 kilometers per hour, this asteroid could smack down right on top of a major city. The amount of energy released by an impact like this would be equal to thousands of megatons of TNT, an event capable of generating massive seismic shock waves, localizing devastating fires, and injecting enough dust and debris into the atmosphere to cause a temporary but severe global cooling event, disrupting agriculture and modern life across the globe. I wonder what would happen if a much bigger object came crashing down onto Earth. How much worse could things get? Okay, it's time to switch things up entirely. What if Earth suddenly shrank to be the size of the moon, and the moon simultaneously expanded to be the size of Earth? This is not just a size swap. This is a total gravitational, atmospheric, and geological catastrophe. How would you be able to fly on this tiny Earth? Why would you eventually never see the moon again? And could humans on Earth survive this catastrophic switch? This is Stellify Science. And here's what would happen if the moon and Earth switched sizes and masses. Here's the new reality, the baseline. Radius is 6,371 kilometers. Radius is 37 kilometers, about 1/4 of Earth. Now for the switch, Little Earth, the new moon. It now has the moon's radius, 1,737 kilometers, but retains Earth's original density, as its composition of crust, mantle, and core remains proportional, just compressed. However, to achieve the moon's radius, its total volume drops dramatically. Critically, its mass would only be about 2% of the original Earth's mass. Big Moon, the new Earth. It now has Earth's radius, 6,371 kilometers. It retains the moon's lower density, but its sheer size means its mass is now about 2/3 of the original Earth's mass. Little Earth would now become a moon of the big moon, and it would start to orbit around it. But first, we must confront the most immediate, life-altering change: gravity. For any celestial body, the force of surface gravity depends on both its mass and its radius. The formula dictates that even though the little Earth's radius is much smaller, around 1/4 of the original, its massive drop in mass to only 2% of original Earth dominates the equation. This is a massive change that would definitely make your life harder, or rather, much lighter. On this little Earth, you would feel incredibly light because gravity would only be about 27% of Earth's original gravity. If you were a 70 kilos person on regular Earth, you would now weigh only about 19 kilos. This new low gravity would immediately feel liberating. Moving around would be like performing constantly, slow motion ballet. You'd feel like Neil Armstrong bouncing around on the moon, only you'd still be on Earth. and you wouldn't need a spacesuit yet. Places that used to be far away would suddenly become so much closer in travel time. The distance between New York and Paris, for example, is no longer 6,000 km in a 7-hour flight. Now, it would be compressed to just 1,500 km. It would take less fuel for aircraft to get there, but also less fuel for launch into the sky, thanks to the massive reduction in required escape velocity. It would become significantly easier to reach orbit. It's great to weigh less, float around, and get to Paris in no time at all. But I'm afraid this fun would quickly turn into a physiological nightmare. We humans evolved on a planet with a gravity of 9.8 meters per second squared. We are not adapted to living in a low-gravity environment. Our entire skeletal, muscular, and cardiovascular systems are built to constantly fight against the Earth's strong pull. The damage would begin immediately. Your spine, no longer sufficiently compressed by gravity, would begin to break down and lengthen. You would suffer chronic, debilitating back pain as your vertebrae and discs swell. Your muscles would atrophy rapidly. Over the course of just 6 months, astronauts in zero gravity lose 13% of their muscle mass. And while little Earth is not zero gravity, the effect would be similar. Furthermore, with less gravity to pull fluids down, your body's liquids would redistribute. Blood and lymph would move up the body more easily, resulting in a condition scientists call the puffy face, bird leg syndrome. Yes, it is exactly what it sounds like. You'd have swollen, reddish faces and dramatically thinned tiny legs. Critically, this fluid shift would increase pressure on your brain and eyes, potentially resulting in a damaged vision and chronic headaches. Survival would be physically taxing, even before the other catastrophes hit. Meanwhile, the big moon would now be as wide as Earth and would weigh about 2/3 as much as the original Earth. Its density is lower than Earth's, but its immense size means its gravity would increase by a lot too. Right now, the moon's gravitational pull is only 1.62 meters per second squared, or about 16% of Earth's gravity. But with this new size, its gravitational pull would become a substantial 5.96 meters per second squared. That's like 60% of regular Earth's gravitational pull. While there is no life on the moon that we know of for this to affect, its newfound gravitational strength would create utter havoc with something on little Earth: the tides. On the regular-sized Earth, the tides are typically 1 meter high, give or take. Tides are caused by the gravitational difference between the near side and the far side of Earth relative to the moon. Now, with the big moon's mass increased by a factor of over 50, it would pull dramatically, violently, on the surface of little Earth. What used to be a gentle daily tide would now be a monumental hyper-tsunami event. Tidal bulges would surge to incredible, lethal heights, potentially tens or even hundreds of meters. Say goodbye to coastal cities like New York, Venice, Tokyo, and London. They would be flooded and instantly wiped out. Millions of people living near any large body of water would die in the first days of the switch. And that's only the beginning of the tidal effects. The gravitational force from the big moon would pull so hard on little Earth that it would literally deform the Earth's surface, and worse, its interior. This is a phenomenon known as tidal heating. The constant, immense flexing of little Earth's crust and mantle, caused by the big moon's increased pull, would generate massive friction and heat beneath the surface. This effect is similar to how Jupiter causes extreme volcanoes to erupt on its small innermost moon, Io, the most volcanically active body in the solar system. On little Earth, this tidal flexing would cue massive, frequent earthquakes, magnitudes far exceeding anything we currently experience, and extreme, explosive volcanism all over the planet. The surface would become a hellscape of constantly shaking ground and continuous violent eruptions, injecting vast quantities of ash and toxic gases into the already rapidly thinning atmosphere. Now, remember I said, you wouldn't need a spacesuit on this new little Earth. Yeah, forget that. You definitely need one. We are able to survive without one on Earth because our planet has a wonderful, thick atmosphere. It has oxygen for you to breathe, and it protects you from the sun's harmful radiation. But on the new little Earth, we're going to lose our atmosphere. And this would happen really quickly for two immediate reasons. The first and most immediate one is the lack of sufficient gravity. Regular Earth's gravitational pull is strong enough to hold the atmosphere in place, resisting the constant thermal pressure that tries to push gases into space, a process called Jean's escape. With a sudden, massive drop in gravity to only 27% of its original strength, the upper atmosphere would immediately start to thermally drift off into space at an accelerating rate. The most common atmospheric gases, hydrogen and helium, would be the first to go, followed by the lighter noble gases. But the heavier gases, like nitrogen and oxygen, would follow soon after. Ironically, the big moon might actually pick up some of these escaping gases. Its new, stronger gravity field could capture the stray atoms and molecules. And who knows, maybe this gray rock, now a massive planet-sized body, would become the newest, most livable place in the solar system once we deal with its own problems. Even if little Earth held on to a little bit of its atmosphere initially, there's a second, more fatal problem that would hack away at it over a slightly longer period: the thermal death of the core. With its significantly smaller size, a quarter of its original radius, little Earth would cool more rapidly. It has far less volume relative to its surface area, meaning heat generated in the core is lost much faster to space. Over time, it would lose all the heat from its molten iron core. This is exactly what happened to the moon when it formed 4.5 billion years ago. It was molten too, but quickly lost its heat. What's the big deal with losing our hot molten core, you might ask? I'll tell you. The churning, convective movement of the liquid outer part of the molten core is what generates our planet's global magnetic field, the magnetosphere. Earth's magnetosphere acts as a powerful shield, helping to deflect and hold the atmosphere in place. Without a functional magnetosphere, the relentless solar wind, a stream of charged particles constantly emitted by the sun, would strip away the remaining atmosphere in a matter of a few thousand years, a cosmic blink of an eye. Of course, losing all of little Earth's atmosphere would mean you wouldn't be able to breathe. But the immediate effects would be even more extreme. As the atmosphere thins and slips away, the temperatures would become extreme, replicating the conditions on the modern moon. During the half-month of daylight, it would get extremely hot, with surface temperatures soaring past 100 degrees Celsius, boiling exposed water. And then at night, the temperatures would plummet dramatically, deep into the negative hundreds of degrees Celsius. Little Earth would likely hold on to its ice at the poles, just like Mars did. But all the liquid water from our oceans, rivers, and lakes would rapidly boil away in the vacuum of space, or freeze solid. And that would pretty much be the definitive end of life on little Earth. Finally, without an atmosphere or a magnetosphere, you'd be exposed to so much harmful, ionizing radiation from the sun that even if you managed to survive the volcanoes, the earthquakes, and the tsunamis, you would suffer immediate, lethal cellular damage. Cancer rates would be 100%. Your nervous system would get fried. Survival on the surface would be utterly impossible. While little Earth would lose its atmosphere pretty quickly, our magnetic field would take longer to disappear. It took about 200 million years for the moon to lose its once existent magnetic field. Over those millions of years, there would be another major, final change on this new little Earth. And I mean major. Our Earth would stop being a planet, at least in function. To explain this, I need to roll back a bit. The moon is tidally locked to Earth. By that, I mean, the moon takes the same amount of time to make one rotation on its axis as it takes to do one revolution around Earth. Because of that, one side of the moon is always facing our planet. In our new, massive switch scenario, after millions of years, little Earth would eventually become tidally locked to the big moon. At first, the big moon's immense gravity would make little Earth slow down its rotation. And after millions of years, this Earth-Moon system would reach orbital equilibrium. Only now, little Earth would orbit the big moon, and we would always face this big moon with one side. The big moon would be functionally classified as the planet, and a little Earth, well, we'd be the big moon's moon. With tidal locking, though, one entire half of our planet would never see the big moon in the sky. Furthermore, the length of a day on little Earth would no longer be 24 hours. It could last as long as a month. You'd have half a month of darkness followed by half a month of daylight. On the bright side, all-night raves and pajama parties would last a really long time. Oh, wait. At this point, you'd be long gone, thanks to the extreme temperatures, volcanoes, earthquakes, and even more extreme radiation exposure. Okay, you know what? We're going to stay positive and assume you somehow managed to survive all the initial catastrophic events on little Earth, perhaps in a deep, insulated underground bunker. You'd still be struggling to breathe in a thinning, toxic atmosphere. Your body would be taking a beating from the low gravity, temperature extremes, radiation, earthquakes, volcanoes, and tsunamis. Your life on this little Earth would be miserable. But on the positive side, the big moon would look absolutely awesome up there, in the now thinning night sky. It would glow 4 times as bright as the original moon, appearing massive and dominant. You'd get to see total solar eclipses much more often, as the two bodies are still near the same distance from the sun. But the big moon, now the size of Earth, would start looking like a much more attractive, if desperate, place to be. The big moon would have significant advantages over the dying little Earth. It has a much higher gravity, 60% of original Earth, which is far better for human biology than little Earth's 27%. It is sitting in the exact same orbit, meaning it gets the same amount of solar energy as we are used to. The two big problems. The big moon still lacks a sufficient atmosphere, and critically, it lacks liquid surface water. So, if humanity, or whatever was left of it, wanted to settle on the big moon, we would have to engage in the most ambitious project ever conceived, building an atmosphere for it, terraforming. One way we could begin this is to deliberately fracture the big moon's crust to release gases from underneath it. Gases that may have been trapped by the planet-sized moon's sheer gravitational pressure. And the fun part? We could initially do it with carefully targeted nuclear devices to break up the dense rock formations. With the new, higher gravity, the big moon would have a much better chance of holding on to this new, artificial atmosphere. Then, with a basic, thin atmosphere in place, our next step would be to extract the immense water ice that we know is hidden at the lunar poles. The regular-sized moon has about 6.6 billion tons of water ice at its poles. But of course, with the new big moon's massive size, there would be several times more water ice than before, providing the foundation for oceans and lakes. After freeing up the water, hardy, radiation-resistant plants could be introduced to produce more gases and slowly begin the arduous process of creating oxygen. The first steps toward a viable, sustainable moon base. Now an entire new world would be in place. But how would we transport the supplies, the seeds, and the humans to the big moon from little Earth? Well, one final bit of good news is that with little Earth's lower gravity, it would take a lot less fuel, and thus less expense, to launch a spaceship to the new moon. The challenge of escape velocity is dramatically reduced. We could use advanced Starship-type technology to make a continuous shuttle service to establish a settlement on the newly expanded, higher gravity moon. The last great migration of humanity would commence, fleeing the dying husk of little Earth. So, maybe humans will somehow find a way to survive. We've survived catastrophes before, and hopefully, we will again. But what if, instead of trying to establish a new home on the big moon, we doubled down our efforts to get to Mars, which would be just as viable and a much safer distance? Well, that's a story for another Stellify Science What If.